Start now? Morning, everyone. Hey. So, enjoyed day one? Excellent. Yeah. So, there was. Day one was packed full of talks. I think today is packed full of talks also. So I think it should be another exciting day. Today I'm going to talk about something that has been actually I've been doing for a long, long time. So I finally decided to write a talk about it, and that's what I call the trouble with memory. I think the issue with memory is that memory chips just simply haven't been getting really that much faster over the years. Yet CPUs still seem to be getting faster and faster, even though the clock rates have leveled out on them, and that's actually created some interesting problems. What I heard yesterday. Sorry, I'm going to claim jet lag. There's no way they should be putting West Coast people in morning sessions at these. Where's Mateus? Mateus, right? West Coast people. Afternoon. We'll do better, right? Because right now, parts of my memory are just blocked off because they're still sleeping. I gave him a scare this morning because, anyways. So there's going to be a number of talks this morning. So as you can see from what I call my marketing slide or whatever, there's one little piece missing, and that's the little company that I co-founded in August was acquired by Microsoft. So I now work for Microsoft, even though my slide deck sort of hasn't been translated maybe all that well. So in terms of memory, I think there's a couple of other talks of interest today that you might want, that I need to shout out, I guess, and that's my microphone is dropping. Of course it's dropping. And it's really broken or something. Whoa. Sound guys, there we go. Just now, see, look, we put us on in the morning and we break all the equipment also. There, that's what it sounds like to have a microphone repaired. How'd that? Did I do a good job breaking it? Yes. Well, that's generally my job, is to break things, right? So, there we go. Okay, so I need to shout out to Monica Beckwith, who's also going to be talking about memory things. I think hers is more around the garbage collection side. So a colleague of mine now. Charlie Gracie is also now working for Microsoft, a VM engineer. And I think he has a talk about things that pause and why they matter, based on some models that we've been building in terms of microservice architectures. And we have a new guest here, well, not new, an old guest that has decided to return to the circuit, Cameron Purdy, and he's going to be talking about XTC. No, not the drug, but actually a new runtime, which actually offers some interesting possibilities. So that's my marketing spot. So I'm going to say, what is your performance trouble spot, right? So normally you could have a quiz here and you can say, okay, what is your normal performance trouble spot? But I bet you can guess, maybe by some of the hints I've given so far, as to what I think your performance trouble spot is. So we'll end that part. But we will go with this particular chart. Oh, there. Okay. So this chart's a bit dated now, but I think the results still apply. And you notice the size of the bubbles in the bubble chart here, and the names of the problems, right? This is a survey that was done by Rebel Labs, and they just asked customers, what do you think your performance problem is? What's your primary performance problem? This is the answer they got, right, from all of their customers. Now, we look at memory, statistics about how applications use memory, primarily from garbage collection logs from applications everywhere. Everybody keeps sending me garbage collection logs, and I keep doing pretty much free analysis for them. And these logs come from just about every possible place you could imagine. As I like to say, I think I probably have the largest collection of garbage collection logs on the planet. Most of them are on this laptop here. It's sort of a hobby, I guess. Anyways, so And invariably, what we find is that's the largest problem. So, if you look at this, I can ask the question, does anyone here know what the memory churn rate is on their application? Let's see. Oh, okay, we have a non-zero result here. Okay, that's abnormal. So we have one person that actually, okay, and I actually recognize that person too. So, okay, so he's probably heard me. Yeah, I've probably bored him into looking at that number by preaching to him at some bar someplace. Anyways, so the excessive memory churn seems to be a problem in a huge number of applications, and it's simply not visible to us because our observability systems are so poor. They're poor because they're highly biased. Who here uses logging to figure out what's going on in their system? I'm going to say that's probably close to 100%, right? Or, right. Probably we should do the old arm exercise. Who here has working arms, right? There you go. So the thing is, quite a few people do, right? And so what does the logging actually do? Well, it's like, oh, well, we had a problem here, so let's put some log around it. Oh, we had a problem here, so let's put some log around it, and finally, you keep log, 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 and guess what all of that logging actually does? Produces a bottleneck on memory churn for you. And not only that, it doesn't really expose the problem. All you're doing is like, we call it like tuning by folklore or whatever. It's historical tuning, right? So this is the number we've come at by looking at all this data. I'd say approximately 70% of all applications on the planet are bottlenecked on memory. That means like everybody's sitting over there, everybody's sitting over there, and about most of the people sitting over here. Your applications have this as their primary performance problem. And it's what I call a silent performance killer because it's spread evenly through your application, and things that are spread evenly through your application tend to be hard to see, and they tend to be hard for profilers to pick up on them, especially if you don't use the right profilers. I mean, who here just does execution profiling? Do you have a memory profiling as part of your regime? One person. There you go. Awesome. And nothing against execution profilers. They're really great tools, but they're only one aspect of what I would call a regime, a profiling regime, and it shouldn't be the only thing that happens. Right. So, and yes, garbage collection. So I run a workshop, as maybe some of you know, and we have this exercise to say, here's a problem. Like, what's the problem here? I would say I've not seen a group on the planet that has not listed garbage collection as a problem, even though there isn't a problem in any case. It's just the automatic default problem. I mean, we get all kinds of activities driven by we need to do something about garbage collection because it's in it's a performance drain or something like that. And it's like going, no, it's a tail latency event and one that we have a really good understanding of how to control. So no, garbage collection is not the problem. However, hands up, who uses Spring Boot? Right? Cassandra? How about any other NoSQL database? Yeah, all the hands are going up here. Yeah, it's about 10%. So Boot was very popular. Apache Spark. Anybody using Spark? Not so many. Okay, it's hard to see with these big lights up here. Or any other big data framework? Yeah, not a large number. I think Spring Boot has actually been the winner so far. Log4j, Logback, or any other logging framework. Is anyone actually using JDK logging? I'll put my hand up. We use JDK logging. You know why? It's actually one less dependency. Oh, look, wow. We have to talk afterwards. You're answering all the questions properly. JSON. Oh. Yeah, XJSON, some other problem? Yeah, talk to Monica, ask her about JSON, right? Actually, when you do, make sure you're far away from her because when she gets upset, it can be kind of like animated. Almost any marshalling protocol you have, ecom caching products, Hibernate, right? So on and so on and so on, right? If you're using any of these products are very, very likely placing you in the 70%, especially the logging. We find that like about 40% of that 70%, you split it up, actually, it's kind of like a bad math, sorry. But, more than half of that 70% comes from logging frameworks that we're using, right? So you really need to be careful about how you use these things. And it's really not that any of these frameworks are bad, except for logging, right? And they're all useful, and we should continue to use them, but we have to be aware of what our primary bottlenecks are, and try to work on resolving them, because that's where we're going to get our biggest performance boost. And when I say biggest performance boost, who here is happy if you get like a 5% performance increase? Maybe 10, right? So if you're getting like 5 to 10% in your applications, more than likely, you're tuning past the bottleneck. Because if you're tuning at the bottleneck in most of the applications that I've seen, you're not getting like 10 or 20%. We're getting like 2x or 4x improvements in performance. That's how bad this problem really is, right? So, so this comes into war stories, right? Who's got the good war stories? Well, here's some of ours. And, I don't want to really go into detail into all of them, but, you can see that there's been some tremendous performance improvements that we keep getting simply by finding the primary bottleneck and tackling it. And in many cases, the primary bottleneck has just been simply allocation pressure. So let's talk a little bit about what's going on here, and so we can try to identify what it is that we're actually. Hello, microphone. Okay, this is a good day for Mike. Is that? I have to shout loud, I guess, or something. Where's our AV guy? Hello? Okay. Woo! Finally, I get to do that. Okay. Okay, here's some code, and there's some bytecode, and you can see what this thing, what the bytecode here is actually asking for is like an allocation to occur. Now, these allocations will mostly occur in Java heap, and there's a couple of different ways in which the allocations can occur. You can get what's known as fast path or slow path. And it's even possible that Hotspot's going to be clever and is going to look at this and go like, I know what you're doing. I'm just going to unbox these values. And as I unbox these values, what I'm going to do is I'm just going to do what this thing called scalar allocation, which means I'm not going to actually allocate on the heap, which means I'm not going to get the heap pressure that's generally responsible for the problem. So small objects with only primitives are likely to be basically replaced with a scalar allocation under certain conditions. It doesn't happen all the time. So if we look at heap, just to remind you what Java heap tends to look like, so we're going to have some Eden space, we're going to have something called a survivor space that's going to make up a young generational space, and we're going to have tenured space. So you can think of Eden as really being our nursery, or survivor space is a place that we just want to keep things until they age, and after they've aged after they've passed a certain age, then we're going to say, oh, that's long term, so we're going to push that off into tenured space. Now, as you can imagine, because each of these spaces plays a different role in the life cycle of your data, there's going to be different problems coming from each of these different spaces if we get into a condition where we're going to abuse them, right? And the net effect is they're all going to affect GC overhead. So the garbage collector is getting blamed for doing its job and doing it as well as it can, when basically you're sitting in the corner and beating it up and going like, okay, you need to work faster, you need to work better. Meanwhile, I'm just going to pound you, keep beating up on you. So let's take a look at an allocation here. So we have two threads they want to allocate in the nursery, or the Eden space. And so what we're going to do is we're going to have a space here, and we're going to put on here like a top of heap pointer. And we're going to have thread 1 go first, so we're going to execute this foo equals new foo, whatever that looks like. Doesn't really matter. First thing we're going to do is we're going to allocate this thread local allocation buffer. And so you can see that's generally it's a 1 meg allocation to start with, and you're going to pop a top of heap pointer that basically tracks, how much memory we've allocated. And then I'm going to put in a TLAB pointer, I'm going to have the TLAB pointer grab the memory for foo, and then we're going to drop the data in for foo into this particular TLAB. Now, thread 2, when he starts to running, what's going to happen is that I'm just going to now allocate a TLAB for him, for that particular thread. And yeah, I think threads are not really male or female. So anyways, we'll just say that thread. And again, same type of activity. We're going to bump the TLAB pointer, grab the memory that we want, and basically put the data in for there. Now, we also have this other allocation over here, and we're looking at this and going like, okay, that's too big actually to fit in a TLAB. Okay, so if n is greater than basically TLAB size, we get a problem. And so in that particular allocation, what I'm going to do is I'm going to bump the top of heap pointer, and then I'm just going to grab the data, the space for the data, and then by bumping the top heap pointer, and then just going to allocate into that particular spot there. So that covers most of the allocation cases that you run into. Now, this all works very nicely because you can see that everybody gets their own spot, like in my own buffers and stuff like that. And when I fill my buffer, then I can go off and get another buffer, and I can keep filling that until I filled up all of Eden. Then, of course, we get a garbage collection running, which gets into this point, right? We have two types of concurrency happening here. We're going to have concurrency with our mutator threads, or what's known as our application threads, right? So it's quite possible that your data is only visible by a single thread, which is, in this case, going to be your mutator thread, your application thread. But all data is visible by at least 2 threads. It's going to be visible by your mutator thread and by the garbage collection threads. And because of that, we need to put all kinds of barriers in here to start making sure that the data is visible, right? Things don't get hoisted in a cache, left in cache, and all of these other things that happen that make your applications run extra fast. So you have to think about, right? Every time I create one of these things, I'm going to be running through these load store barriers. Every time I access these things, I'm going to be running through some read barriers. So there's all these barriers that are there just to actually help the mutators interact with the garbage collection threads or any other like JVM threads that might be running around. So it's not just mutator threads in this case, it's other threads. Okay, so you can imagine with the TLABs, what happens is we're finally going to get to the end, and there's going to be this thing called the TLAB waste percent. And so what the TLAB waste percent is, like if I'm past that, don't bother trying to allocate here, go get me another TLAB, right? And you really want to try to prevent buffer overruns, but you can get into this condition here where you're not past the threshold, but the thing you're going to allocate is bigger than what you have left, and that's actually going to push you into what's known as a slow path allocation, because now I basically have to go out and do some calculations, look at it and go, oh, darn, buffer overflow, don't want to do that, so I need to now go get another TLAB, so it's slightly more expensive. In Tenure Space, there's 2 ways that we manage Tenure Space. One way we do with G1 is that we're actually going to end up copying data around, and that with the data copying activity, we end up getting what's known as a natural compaction in the in that particular space. For generational collectors, parallel, serial, or whatever, we're actually going to use a free list. So we have to do all of this free list maintenance. And the free list maintenance is actually expensive. So if we, so the 4th type of allocation that we're going to get is an allocation directly into Tenure Space. Generally, that's the garbage collection threads that are going to do it, not your mutator threads. But if you allocate something large enough that it doesn't actually fit into the nursery, then your mutator thread is actually going to do the allocation right out into Tenure Space. Now, for G1, that generally is going to be qualified as a humongous allocation, which comes with its own set of difficulties. But really, what we're saying is that this is a far more expensive allocation because it's no longer a bump and run on a pointer. We have to do a whole bunch of work with free lists. and free list maintenance and things like that. Okay, so what are the problems that we run into here? Well, with high memory churn rates, we are going to create many, hopefully, temporary objects that if your application is following like what's known as a weak generational hypothesis, in other words, most data is dereferenced before it leaves the CPU, therefore dead. Right, so the collectors are optimized in that direction. So if most of your data is long-lived, then you're going to run into a whole different set of issues, which is another talk, which we won't get into here. But you can see with high memory churn rates, we're going to quickly fill Eden. We're going to have frequent young GC cycles. And this is actually going to speed up the aging process. As I like to say, we have two clocks working here. One is the wall clock time. Generally, your application threads are going to live by wall clock time. Your data is going to live by wall clock time in that particular space. We also have this notion that your data ages as it survives garbage collections, right? So it's a completely separate clock. So the behavior of where I live in heap is going to be governed by the second clock. My data is going to age by the number of collections it survives, right? So what I can start doing is I can start, so I got this curve of data that says, it's going to live for this particular length. The question is, if it lives for a minute, is it going to be in young generational space or is it going to be in tenured space? I have no idea, right? What I need to know in order to make that determination is to actually understand how frequently is the garbage collector running in that 1 minute period, right? So we sort of have these two weird timing things that collide in strange ways. So you can control the age by simply playing with the size of Eden. And of course your allocation rates, right? So if you speed up the aging, it's very likely you're going to get short-term or temporary data actually being pushed out into tenured space. It puts more pressure on that space, and you get more copy costs. You have to collect tenured more frequently. You get increased heap fragmentation, which means you're going to have to do compaction more frequently, right? So you can see, so what you're seeing here is, the point is that all of a sudden this high frequency of allocations with an improperly configured heap means that I'm actually going to end up with a whole basket of problems. Not just a single problem, it's going to be a whole basket of problems, and each of them are going to be a latency hit for you, okay? And that doesn't take away the fact that, but as you can see, the allocations are very quick. It's just a bump and run on a pointer. It's very, very quick, right? But quick times a large number equals a long time, right? So I give you an example. We once ran into a problem there where we had database transactions, right? Database transaction was taking 2 milliseconds. Anyone here going to complain about a 2 millisecond database transaction? Generally not, right? The problem is they were doing 20,000 of them sequentially in order to fill a page. So now you go 20,000 times 2 minutes. Oh, that's 40 seconds. Right? Anybody going to complain about a 40-second database transaction? Hands up. Yeah, okay, there we go. Right? So, quick times large number, slow. And that's really another issue here. So you really want to go and try to figure out, okay, what's my hot allocation sites and what can I do to cool them off? Because this is the type of curve that we see. And by the way, you might say, oh, well, I got this big fast Xeon processor with quad socket, whatever, 2 gazillion core thing happening here. So, I can possibly sustain a higher allocation rate. And the answer is, no, it doesn't really seem to matter what hardware you're on. This curve seems to hold fairly true across a whole front of hardware platforms. Right, but basically, as you can see, what we want to do is if we're above a gig per second, that's our magic number, I want to drive that down because I know that there's going to be some significant performance improvements when I start driving that curve, driving down towards the 300 megabytes per second. Second problem, mostly to do with tenure here, live data set sizes. If you have large live data set sizes, then you're actually going to start making the garbage collector do a lot more work, right? So we're going to get inflated scan for root times. So every time I do a young generational collector, I need to calculate the root sets and tenured, as one of the spaces. So larger, right, means more work. Reduced page locality, inflated compaction times, increased copy costs, right? And if your heap is improperly configured, there's likely less space to do the copying, and which means it's got to do shuffling and all kinds of weird things, right? Fragmentation is now going to be a bigger problem, right? So you can tune the memory spaces to try to minimize these problems, but basically if you have a high allocation rate, you're still going to have these problems, these other problems that are going to come from that, which really means the primary problem, the thing that the pressure valve here that you basically need to get to is the allocation rate. So if you look at pause time versus occupancy, we've got nice charts here. So the left, just look at the red dots, right? They form a line, and that's my live set size in this particular heap space. If I look at the chart on the other side, heap occupancy chart on the other side, you can see that's my CPU times, essentially, or the latency, the amount of time for the garbage collection run, right? Pretty much a one-to-one correlation here. And that's in a well-tuned collector. And then we get into different pathologies, right? So if you have an unstable live data set size, or commonly what's known as a memory leak, or maybe we have, eventually you're going to run out of heap. And the problem, aside from that, is that it's almost impossible to tune the collector appropriately. So there's another chart that I've recently drawn I should have put in here that shows basically the effect of heap size on performance. And, and the curve, so if I can just draw it by hand, goes like this, and then it levels out, and then you start a slight decay like this. So there's an optimal heap size that you want to work in. And if you have a memory leak, you can't tune your heap because your heap is just going like this. So, or do you tune for small? Do you tune for big? Do you tune for somewhere in the middle and hope? Essentially, this is another pathology that you need to do something with, and again, that's another talk. Okay, now finally, we need to talk about this thing called escape analysis. Do you have a time on that thing? Sorry? 20 minutes. Okay, good, excellent. So a little bit about escape analysis. So has anyone here actually been playing with like Growl VM? Few people with the OT stuff? Not too many, right? Okay. So one of the emerging battles seems to be is in the area of escape analysis, because escape analysis is so what is escape analysis? Well, it's basically looking at a piece of data and saying, okay, I have this piece of data here. What is the visibility of this data to all of my other mutator threads? And if the answer is I have no visibility here, then I am free to do a lot of optimizations. This is where the scalar replacement comes from, right? Or what we've been working on, which we call like stack allocation. Actually, Charlie has been working on. We're free to do these things because we own the data and no one else is going to see the data, so we can basically do whatever we want. And so we can get rid of the allocation site, assuming that the data doesn't escape. Now, there's many different ways that it's going to escape, and that depends upon how you do the escape analysis. With Growl, we're using a tracing method for escape analysis. So the escape analysis right now in Growl VM is actually better. And so they can get more data to escape, which means that they can provide more optimizations around this particular problem. Hotspot, we're trying to catch it up right now in terms of making better escape analysis, because in Hotspot it's stack-based. So basically, all it can see is what's in a method. This is why the other optimization, known as inlining, so call site reduction with an inline of the code, is important, because that makes your event horizon bigger, which means I can find more opportunities to do the scalar replacement, or in our case, the on-stack replacement. Right? And that takes pressure off of the heap. So that's going to actually help with performance somewhat. Actually, quite a bit. Anyways, the point is, this is a very important technology in helping us resolve at least part of this issue. Okay, now, and that gets kind of important because one of the reasons that things can escape is because I've passed, in hotspot, I passed this thing on as a parameter to something else. Now, and that becomes a problem because, okay, so how are we going to find our allocation hotspots? Once we've recognized we have an allocation hotspot, how are we going to find it? Well, typically we're going to use a memory profiler. If we use a memory profiler, the traditional memory profilers, then what happens is that we're going to inject, an agent's going to run, it's going to inject code into the runtime, and it's going to do some bytecode manipulation, it's going to basically wrap the allocation. As soon as I've wrapped the allocation, that means I'm going to use that data and I'm going to pass it off to something else where the profiler threads have visibility to it. So what has that just done to escape analysis? Right? Gone. All of a sudden, our application, which runs one way in our production system, as soon as we start to put a profiler to it, starts running differently. And it's quite fun. So in the longer version of this talk, I can actually go through it. We actually have a hot site, which is perfectly scalar replaced until you put a profiler on it. And the profiler comes up and basically says, that's your hot allocation site. You go into your application, you fix the code, and guess what happens to the performance? Anybody want to shout it out? Nothing. Did I hear someone say nothing? Makes no difference whatsoever because hotspot is actually eliminating that allocation site for you. So it's basically fixing your less than memory efficient code for you, right? Put the profiler on it, all of a sudden it can't do the work anymore. And so the profilers, this is one of the ways that profilers actually will mislead you. What can you see? Oh, right. So I have this funny little application here. And it's a game simulation. It's basically going to, we're going to play some mastermind, but instead of using colors, we're going to use numbers. If you don't know what the game is, you can Google it and play it online. But it's a guessing game. So I'm going to give it a pattern. And it's the program's responsibility to find this particular pattern. So in this case, I'm going to pick 3 numbers from 100,000. It's like a lottery, I guess, right? And so the question is, okay. And so it's going to make, oops, let's fix that. It's going to make some guesses. And as it makes guesses, we're going to score the guesses. Right? So here it is, it's working away. So it's made a guess. It says, I think it's 0, 1, 2. And which I answered, yep, you got one of the numbers right, and it actually happens to be in the right column. So it runs and runs and runs and runs and runs and runs. And maybe eventually it'll finish. It's always a good time to take questions. Running performance benchmarks are, just really fun. Any questions so far? It's running. This is what I do at home, right? I run benchmarks like this. My wife comes into the office, she said, what are you doing? I said, running a benchmark. Even if I'm not, because she knows running a benchmark, oh, I need to go away, right? If I don't say I'm running a benchmark, then she says, oh yeah, come out here and do this for me, please. So it's really kind of, okay, here we are, we're fine. Don't tell her that. This is not being recorded, is it? Okay. Okay. Yeah, so this is 67 seconds to actually come up with the answer. So that's the pattern that we're actually looking for. This is really cool. So what is the, so what's the performance bottleneck in this application, if you can't guess, right? Don't look behind the door, right? Well, let's pretend we don't know. So we have this wonderful tool that we wrote that I used to be able to give you, but unfortunately I can't for a while because it has to go through some sort of Microsoft compliance thing. Sorry about that. There are some replacements which are less good, but sorry, I'm biased. Okay, short story, because I don't know how much time we have. Let's just look at the allocation rates. And you can see that I have consistently here, I have an allocation rate at about 7.5 gigs per second, or thereabouts, do the math right. Okay, so what was the number? What was the magic number we gave you before? 1 gig per second. So that's way above, right? So it feels like there should be good opportunities here by reducing allocation rates. So now I need to find the hot allocation site in this application. Anyone want to tell me what it is? Yeah, uncomment that line. Yeah, exactly. I was having trouble with Visual VM this morning. It was just like when I was just making sure the demo actually was behaving properly. Oops, hold on. Let's get this thing to run. Yeah, we're going to use a memory profiler. Of course, the memory profiler is going to get it wrong, but we'll get past that quickly because I want to leave time for some questions. And oops, oh, I started it too. Where is it? I should have attached first. Oh, well. I'm doing this wrong. Please don't do it this way at home. Should get the memory profiler attached before I actually attach. It's going to attach. If it's not doing anything, it will attach faster. Okay, memory profiler, any profiler, make sure you understand what your filters are. Make sure you're not filtering your bottleneck out of your profile. Yes, it happens all the time, which is really fun. And yes, okay, excellent. Now, I don't have allocation frequency number, but I do have allocated object counts, and with allocated object counts, I can sort of use it as a rough estimate of allocation frequency, okay? And you can see I got an index on top here, and I have an int array. Let's take a snapshot so I can get away with, normally you need to let the thing develop, but with this app, we don't really have to. So let's take a look. So there we go. That's the problem right there. We have this class here, arrangement group, and it's trying to remove a symbol, whatever the heck that is. Don't know, don't care. But this is my top hot allocation site. Okay? So what do I want to do here is, well, I want to go into the code, and I want to try to fix the code. Now, the code here is a bit complicated because it's actually doing some funky things with indexes and converting them to base 100,000 choose 3 numbers. Anyone figure out how to do that quickly? So let's just go over to our particular application, and we can actually look at the code. Here, let's abandon that. Oh, yeah, abandon, hello, exit. Yeah, this is the problem I was having before. It wouldn't actually stop, quit. Not stopping, are you? Okay. In that case, don't want to go away? We'll just do it that way. That's our kill -9, right? Don't do this at home. Ignore, I don't care about that. That should be detached. Okay, so where's our arrangement group? So it's our arrangement group. It's like calculate index. There's some goofy things over here. We've got a bit of goofy code here. Without doing too much of the analysis, which take a bit of time, you can see that, yeah, this is my remove symbol that shows up in my profile. And so I can just run through here, figure out what the heck this is doing, or I can do what was suggested before, which was replace the implementation. Right, so now I've gone through the process of fixing the implementation where I have this version of it down here, which doesn't call that goofy remove symbol thing. So hopefully this all works better. Okay, so there we go, same problem, run the tests. Right, we were at 60 some odd seconds before running. There was a long pause, right? It was a long, uncomfortable pause. Excellent. And right, there we go, 3.5 seconds. Rocks, right? It's likely that a portion of that 3.5 seconds is due to, I got the 10-minute sign, thanks, is due to other things that I was doing that were kind of stupid, but anyways, you get the point here is that we didn't actually just simply get like like 5 or 10% improvement in performance. We end up getting very significant performance improvement, and this result is quite typical of what we're finding when we're actually able to apply these type of optimizations out in the wild in real applications. Because you're going to say, "Oh, my application is bigger." It's like, no way this can happen. The answer is, yes, actually it can. Right. Okay. So, cool. So, how do we know it was allocations? Well, we can go back, and I'm going to basically do my analysis on the GC log again. Bring it up, and you can see when we come down to allocation rate, boom. How's that? Notice there's also a lot less garbage collection activity, right? The other chart was a lot heavier, more heavily populated with data points and things like that. So but actually it wasn't that GC efficiency was so bad. I probably should have showed you the GC efficiency number. It was certainly above 99% GC application throughput, which is like, well-tuned collector. In this particular case, if we look at the summary, it's like, okay, 98.5% application. So well-tuned collector. This collector is doing very, very well. Oh, by the way, for most applications, the default configuration out of the box for the JVM, is suboptimal. I was going to use a different word, but I'll use the polite word here and say it was like very, very much suboptimal. Excellent. Okay, so yeah, sorry, back to slides. Terrible. So I guess if you look at the demo and everything like that, okay, demos are always contrived. We know that we're going to get the results, but this is something that we seriously looked at. If you look at Spark workloads, I know there's only 1 or 2 people using Spark here. As a matter of fact, is anyone using like Kotlin or Scala? These type of languages? Few, not too many. As far as I can tell, it's hard to tell because of how the lights are. Can't really see you. So the thing is, like, a lot of the allocation site reductions actually happen because Hotspot is tuned to recognize idioms or programming idioms that are Java programming idioms, not Scala programming idioms, not Kotlin programming idioms. So you sort of get a loss when you go to these other languages simply because, the idioms are slightly different. Plus, Scala, being functional, more of a functional language, tends to encourage escape analysis failures. So we tend to see a lot higher allocation rates in these languages than we would in just a pure Java application, just out of the box. Now, you can tune the heap to try to hide some of that, but at the end of the day, it really comes down to these languages are just not as well optimized by the runtime, which means you don't get as many allocation site reductions as you do in other different workloads. If you want to understand more of this, it's more of another talk. I would suggest maybe you look up Chris Newland on the web. He has a wonderful tool called JITwatch. You can see what the Hotspot compiler is doing, how it's going to log every activity that it's doing, and you can use JITwatch to actually load these log files up. And it actually has one little analytic in there which basically says, where are my allocation sites? Where they've been reduced? And if they haven't been reduced, the question, you can ask the question, why? Well, generally, in some cases, the tool will actually tell you, I couldn't get rid of this allocation site because, whatever the reason was. I had a partial escape or something like that. Right. So that's the end of my ditty about memory efficiency and memory efficiency in, the importance of memory efficiency. I think I wanted to leave a few minutes at the end for questions. And it looks like I've succeeded. So I will take questions from anyone who's willing to ask. I know it's Sweden. People don't like asking questions, but, maybe there's non-Swedish. Any non-Swedish people in the audience? Okay. Do you want to ask the first question then? That's okay. Yes?
Mike? No?
Mike? I'll repeat your question. Just shout it out.
excessive memory allocation and the effect on caches.
Oh, right. So the question is excessive memory allocation and the effect on caches, right? And I should probably put that in a list, but that sort of gets into like hardware level effects of this. Yeah, so certainly higher memory pressure is actually going to result in you overflowing your CPU caches, which means you're going to end up getting a lot of cache misses. And gosh, yeah, again, morning talks, not great for people on West Coast, but somebody described your CPU as going like, that's good, your memory doesn't work, right? I was rapping in Poland, by the way, for something like that, so. So I'll do silly things anyways. Yeah, so it's like, one step, and then all of a sudden you're blocked for like 300 clocks while you go off to main memory to get things, right? Oh yeah, that's right, and yeah, the most important point, right? So if you want to sound really intelligent, then you can go back to your colleagues at work and say, do you realize every allocation is a cache miss? Right? Now, I don't know why that is, but it sounds really cool, right? But effectively, so when we do the allocation and create the allocation sites, that data is not in cache, so we have to go and do things and get things, right? So, and again, if I have to go off to main memory, that's glacial. That takes a long time. You're going to stall your process for a long time. So if you're using perf on Linux and stuff like that, you just watch your instruction retirement rates, because they're just going to tend to go like, drop like that. Good question. Thank you. Anybody with a second question? No. I could have added more slides then. I think. Everything. Great. Oh, I have a question up in the back. Shout it out, please. Someone's talking about, sorry, can you shout that louder? I heard something in the neighborhood of mutable objects, or immutable objects. Ah, lovely immutable objects. So this is the fun part, right? So immutable objects actually, copy on write actually is a problem because, of course, if I'm going to mutate, I got to make a copy. That means cache miss because new object, change state. And yeah, so this is a known problem. But here's the fun thing, right? A lot of the JDK data structures that are copy on write, what happens is that when Hotspot looks at this thing and starts ripping it apart, it says, oh yeah, no problem, I know what this is. I'm going to turn this immutable data structure into a mutable one. So if you look at things like on copy on write array, which actually I use in here because I was going like, I'm clever, I'm going to put a copy on write on there and we're just going to make the memory pressure go like through the roof. And you run it and go like, that didn't work, what happened? Hotspot study, you look at it and go like, oh my God. These guys are really smart. They realized this was going to be a problem, so what they did was they replaced the entire implementation with a mutable data structure. No memory pressure. We're done. That's really cool. Now, if you go into, again, other runtimes, then it's like a not so much case, because and if you write your own immutable data structures, then unfortunately it's likely going to be a not so much case. So they've optimized for the common cases, but they actually haven't provided this optimization in a quote-unquote more generic way. And it looks like I have time for one last question. Does that answer your question there? Okay. Cool. In that case, you may have 1 minute of your life back. Thank you for attending.